So this time we're going to get into the constitutive relationship. Sounds like a novel by that. What's that guy's name? It doesn't matter. Like the Pelican Brief, the constitutive relationship. Okay, so constitutive is like the material's constitution, how the material is constituted, and it describes the relationship between stress and strain. So relationship between the Voigt stress and the Voigt strain. So remember that we're doing sort of a 3D version of Hooke's law. In physics, Hooke's law said the force applied by a spring is equal to the spring stiffness times the amount of stretch or compression of the spring. Ours is going to look like this. The strain, the Voigt strain, is equal to a matrix C times the stress, the Voigt stress, or equivalently, this is the one we're going to use most of the time, because most of the time the stress is the thing we're going to be able to calculate through other approaches, and then we'll use it to calculate the strain. But you could also do take the take the inverse of the compliance matrix, multiply it to both sides, and you would get that the Voigt stress is equal to the stiffness matrix times the Voigt strain. So this is called the compliance matrix. And this is called the stiffness matrix. And by the way, on the first day of class, I noticed this a couple classes ago that I wrote up this relationship, but I called this the stiffness matrix. So it's not a big deal, but you might want to go back to like the first. It's probably the second day of class. So I did the day where I talked about the syllabus, and then I think it's on the second day. I mean, I was just kind of going through an overview of things, and I gave you a matrix that I called the stiffness when it was really the compliance. Well, for engineering materials, I've asked this question a couple times before. Which of these values do you expect to be high? Compliance values or stiffness values? Stiffness. So, you can see that the values that I gave you and I called it the stiffness matrix, are going to be really small, so it doesn't make sense that that's the stiffness matrix. Okay, so what's the matrix shape of the compliance or the stiffness matrix? I'm going to do the compliance. Well, and I think I've written this before, but let me just get this down here again, where the stiffness matrix is the compliance matrix inverse and vice versa. Yeah. So, and your calculators will do inverses for you. So if you can come up with one of these matrices, then you're good. There's no reason to know the form of the other one. So what do we know about the compliance matrix? Well, what are the sizes of the Voigt stress and the Voigt strain? Yep. So what's the size that you need for the compliance matrix to go from a 6x1 to a 6x1? Yep. So it's a 6x6. So that's 36 values. So potentially each one of these 36 values could represent a different property of a material. And that means that in order to come up with a compliance matrix for a material, could potentially require 36 independent values that represent a material. And depending on what those values are, there could be different tests for all of them, but it's hard to imagine coming up with an easy way if your material is defined by these 36 values. It's hard to imagine all of those being easy things to measure. And so there's the chance here when you look at this for this to be a very difficult thing to measure for a material. For our materials in this class, the 36 values depend on only two independent parameters. And those two parameters are really easy to measure. This is a big deal. And it's not true for every material. And so I need to be really explicit to you about what it is that makes this possible. And so we'll talk about that some today. But these, right, like not all materials have these 36 values determined by just two parameters that are easy to measure. In this class, it's all we'll care about, but you got to know why it is that we can do that, make that simplification, okay? 2 is much better than 36. So here are the two values. The independent parameters are capital E, that's called the Young's modulus. Or the modulus of elasticity. Or the stiffness. So based on the fact that you call this the stiffness, do you expect that number to be big or small? Big, way bigger than 1. For metals, the range is around 100 to 200 gigapascals. Okay, so 100 to 200 times 10 to the 9th pascals. Okay. And the other parameter is called Poissons ratio. It's like poison with 2 S. Yes, it's a Greek V, nu, Greek letter nu, like a script EV. And for metals, this has a value of usually somewhere around 0.3, and it's unitless. You get these two parameters from what's called a tensile test. A test where you put the material in tension. And the way it works is, so you have your sample material, like a long skinny piece of whatever you're testing. And there are clamps on both sides. This shaded red is the sample material. And you stretch it apart, which obviously takes a very strong machine. MTS is a really big company in the Twin Cities. And they started out making these machines. Now they do testing for all sorts of different things, vehicles, all sorts of crazy stuff. But they started out by just making these machines that were, you have to have a lot of precision in, well, yeah, you have to have a lot of strength at the same time that you have a lot of precision to do this right. But when you stretch this, you measure two things. So first let's talk about how to measure Young's modulus. So to measure the Young's modulus, you measure the stress, and I'll call it the XX stress, where I'm using a coordinate system with the x-axis that way. And you measure that if you're applying this force F. Okay. Then to measure the XX stress, you do that as the force divided by the cross-sectional area of the sample. And then you measure the XX strain, which is the deformed length minus the initial length divided by the initial length. And then the Young's modulus is the stress divided by the strain. So you can see if you multiply this XX stress to both sides, you get an equation that looks a lot like the spring equation, where this E is just the spring constant, but our spring is solid material. And you can see from looking at how you calculate it that the units are units of pressure divided by something unitless, so you end up with stuff in pascals or megapascals or gigapascals. To measure Poissons ratio, you take a third measurement you measure how much one of the sides contracts. So let's say measure the side length, and it doesn't matter which axis you use. The side length perpendicular to the loading axis. And then from that, you can measure this off-axis strain. So this would be like, again, L minus L0 divided by L0. But this time we're measuring, so we're measuring a strain, but this time, if you look at this picture, we're not measuring how much this stretches in this direction to get the strain. We're measuring, as you stretch this, how much does it contract in the Y direction or in the Z direction, okay? Every time you stretch something, it gets thinner. And every time you compress something, it bulges out, okay? And that's what we're measuring. How much skinnier does it get off axis when you stretch it? Yep.
Does it stretch equally everywhere, like one in the middle, then on the end?
It does eventually, but not for the region that we care about. So I'll talk about that a little more. And when I say region, I don't mean the region of the material. I mean for the types of loads that we care about for our calculations. So yeah, I'll talk about that in a second. And now Poissons ratio is the negative off-axis strain, normal strain, divided by the axial strain. And you can do it in any direction, so I'm going to say it's also equal to EZZ over EXX. And that negative sign is there because if it's getting longer, you're stretching it, that's going to make it contract off axis. And if you're compressing it, that's going to make that smaller. It's going to make that negative. So yeah, if it contracts this way, it's going to bulge out the other way. Okay, so that's what that negative sign does. It makes Poissons ratio always positive. So the range of possible values. So I said for metals, it's usually somewhere around 0.3. The possible values for Poissons ratio are 0 to 0.5. So 0 would be no off-axis contraction. And 0.5 would be that volume is conserved. So when I say volumes conserved, like imagine a water balloon, full of water. If you squish it this way, it bulges out this way in a way that conserves the volume because liquid is incompressible. Okay. Well, metals aren't exactly incompressible. If you stretch a metal, it's going to contract a little bit, but not enough for the volume to stay constant. Okay. And if you compress it, same thing. It's going to bulge out, but not enough to keep the volume constant. There's no material where you stretch it and it contracts so much that, let's see. So if you stretch it, it contracts so much that its volume is decreased. That never happens, okay? And if you compress it, it'll bulge out, but no material bulges out so much that its volume is increased, okay? So this is the limit that it's incompressible. One sort of interesting thing, one material that has just about exactly 0 Poissons ratio is cork. And if you think about it that way, so if you take a piece of cork and stretch it or compress it, the off-axis side lengths are basically unchanged. And that's a very useful thing if you're taking a piece of cork and a hammer and pounding it into a glass bottle, And so that's why that's a useful thing for wine bottles, because if you took a piece of metal and set it at the top of a bottle and whacked on it, it would compress down, bulge out to the sides, and break the bottle. Okay, so once you have these values, the compliance matrix is this. 1 over E, negative nu over E, negative nu over E, and then 3 zeros. And then the 1 over E for the next 2 rows just keeps moving down the first 3 values, and the other of the first 3 values are replaced by the negative nu over E. So that's the first 3 of the 6 rows. And then for the next 3 rows, all 3 of them have zeros in the first 3 columns. And then 2 times the quantity 1 plus nu over E. And that non-zero value now just moves as you go down the rows. So the 5th row has 4 zeros, and then the quantity 2 times the quantity 1 plus nu over E and a 0. And then the last one has 5 zeros, and the last element is 2 times the quantity 1 plus nu over E. So notice the individual elements of the compliance matrix are tiny. Less than 1 times 10 to the negative 10 for metals. And the units are 1 over units of pressure, which would be like meters squared over newtons, or 1 over pascals. Yep.
So before you're saying like stiffness matrix is big and flat matrix is small, that 1 times 10 to the negative 10 is what you're.
So now we have that the Voigt strain is equal to the compliance matrix times the Voigt stress. And that's the relationship we're going to use in this class. Here are the 4 main assumptions that, you know, in a way, that's kind of like the heart of this class, is this relationship. Knowing what the stress is, knowing what the strain is, knowing how to go back and forth between them. Okay. So here are the 4 main assumptions in this class, and these will definitely be, not today, but these will definitely be questions on quizzes. So keep these in mind. There's, I would say, maybe more than any other bit of information in this class, you need to know what cases what we're learning is applicable to, you know what I mean? So the 4 main assumptions in this class. Okay, the first one is small deformations. None of what we're doing applies to big deformations. And so you can think of strain values as less than about 1 times 10 to the minus 4. And that comes up in a lot of ways, actually. That can mess things up in a bunch of ways. One of the ways it can mess things up is it messes up the second, so these two are somewhat related. The second assumption is that we have linear elasticity. Which is the same thing as saying that materials obey Hooke's law. This is the one that says that the Voigt strain is equal to the compliance matrix times the Voigt stress. Okay, so even if you have small deformations, if you have a material that's really far from linear elasticity, if that linear relationship does not model it well, our calculations aren't going to work very well. The third assumption is homogeneous materials. And that just means that in your hunk of material, if you look here and you look here, any 2 spots have the same material properties. Like homogenized milk is milk that's, they take out the blood and the bugs and or probably they just blend it up actually. But anyways, they make it all into a single consistency, you know. And the fourth one is that the materials are isotropic. Isotropic doesn't talk about two different points, how they compare to each other. It talks about taking measurements at the same point in two different directions. So you have the same material properties in every direction. So if you go back to the compliance matrix that I defined, this compliance matrix only, so this is the form only for isotropic materials. Can you think of a material that you wouldn't expect to be isotropic? So think about things that, like, think about materials that look different in different directions. You know, like, well, like wood. Okay, wood is not usually very well modeled as isotropic because of the direction of the grain. If you apply forces in one direction, it's stiffer than if you apply forces in the other direction. Another thing that you can't assume is isotropic is bone. You know, bones are made to support forces along their length. They're not very good at resisting compression on their sides. And so if you're doing calculations with wood or bone or anything else with a grain, another thing that's not very well modeled as isotropic is stuff that comes out of a 3D printer because it's laid down layer to layer and there's a different strength if you're going in the plane of the layers than if you're going out of the plane of the layers. Now, some of these ideas can still be used on things that aren't isotropic, but usually you just have to do it sort of direction by direction. You can't use the matrix approach. And I'll talk about that more when we get to specific things.